about the behavior of real gases, and also we're going to talk about solutions. So first, let's talk about the real gases. So real gases often do not behave like ideal gases at high pressure or low temperature. So I kind of mentioned this in the last lecture, but sometimes at higher pressures and lower temperatures, intermolecular forces and the size of the molecules do come into play. So ideal gas laws assume that no attractions between the gas molecules, that there are no intermolecular forces between those gas molecules, and then the gas molecules do not take up space. And so they assume that there is little to no volume in those gas molecules, and this is based on the kinetic molecular theory, which we talked about last time. But at low temperatures and high pressures, these assumptions are not valid. So at low pressures, the molar volume of argon is nearly identical to that of an ideal gas. But as the pressure increases, the molar volume of argon becomes greater than that of an ideal gas. So if you look at this graph over here, you notice that as the pressure increases, the actual volume of the argon gas is going to be greater than that of an ideal gas. And this is because at higher pressures, the argon atoms themselves occupy a significant portion of the gas volume, making the actual volume greater than the predicted ideal gas law. So at higher pressures, what's happening is that the pressure is getting higher. These actual argon atoms are taking up space. So the volume of the argon atoms are actually coming into play here. And so the volume is going to be greater for argon than an ideal gas at higher pressures because those argon atoms are actually starting to take up space. Now, in 1873, Johann van der Waal modified the ideal gas law equation to fit the behavior of real gases at high pressures. So the molecular volume takes up real volume larger than the ideal gas would predict. So the actual molecules are taking up volume. Van der Waals modified the ideal gas equation to account for its molar volume. So B is called the van der Waals constant and is different for every gas. So every gas has a different van der Waals constant because every gas has molecules that are different sizes. So basically, if you wanted to find the volume of a gas at a very, very high pressure, you'd have to add NB, where N is the number of moles of gas that you have, and then B is that van der Waals constant. And again, it's different for every gas because every molecule is a different size. Now, at high temperatures, the pressures of gases are nearly identical to that of an ideal gas. But at lower temperatures, the pressures of the gases are less than that of an ideal gas. So at lower temperatures, remember the gas atoms are moving slower. They're moving a lot slower. And so they spend more time interacting with each other and less time colliding with the walls, making the actual pressure less than that of the predicted ideal gas. So this has to do with temperature and pressure. So the molecules are moving less. They're interacting more with each other than the walls because those intermolecular forces are starting to take over. They're moving slower. Those intermolecular forces are starting to take over, so they're not hitting the walls as much as they are interacting with each other. So the pressure is actually going to be lower at a lower temperature. So van der Waals modified the ideal gas equation to account for these intermolecular attractions that are happening. A is another van der Waals constant and is different for each gas, again, because their molecules have different strengths of attraction. So he modified it to where to find the pressure, we take our pressure equals nRT over V minus A, which is that van der Waals constant, but this is because this has to do with the pressure of the gas, not the volume. And then N is number of moles divided by volume, and that's going to be squared. Now, so combining these equations can account for molecular volume and intermolecular attractions we get for the following equation. So we can actually combine these equations to find the ideal gas law for real gases. And so basically it's PV equals nRT, but remember the pressure has to be has to be rearranged and the volume has to be rearranged. So it's pressure plus A. Again, that's that van der Waals constant, which over here is the columns that give you those constants for each gas. And then N is the number of moles divided by V squared. And then volume minus N number of moles B. So here we have A. This has to go with the pressure. And again, this is different for each type of gas. And then over here we have B, which goes with the volume. And again, it's different for each type of gas. And then we plug in nRT. Now, let's talk about solutions and mixtures. Now, you're going to be seeing solutions a lot. Basically, the rest of the chemical reactions that we're going to do is actually going to happen in a solution. So it's very important that you understand what solutions are. So when table salt is mixed with water, it seems to disappear or become a liquid, and the mixture is homogeneous. So when table salt mixes with water, the salt completely dissolves. It's still there, but you can't see it, but you can taste it, or you can simply boil away the water. So homogeneous mixtures are called solutions. So that means it's uniform throughout. We can't see the individual components. Now, the majority component is the solvent. So in this case of salt water, the solvent is the water. And then the minority component is the solute. So in case of this salt water solution, the solute is going to be the salt, and the solvent is going to be the water. A solution in which water is the solvent is called an aqueous solution. So you'll hear aqueous solution a lot. You'll see it in parentheses as AQ, so make sure you understand that. Because solutions are mixtures, homogeneous mixtures, the composition can vary from one sample to another. So we can have two different samples of salt water, and one can have more salt in it than the other. Pure substance has a constant composition, but saltwater samples from different seas or lakes have different amounts of salt. So to describe solutions accurately, we quantify the amount of solute relative to the solvent, so we call it the concentration of solution. Okay, and so this is how we find the concentration. So a common way to express concentration is molarity. So molarity is the amount of solute in moles divided by the volume of solution in liters. So it's the amount of solute, so the amount of salt we have in moles, divided by the whole volume, the total volume of solution. Now, we can use the molarity of a solution as a conversion factor between moles of solute and liters of solution. For example, a 0.5 molar sodium chloride solution contains 0.5 moles of sodium chloride for every liter of solution. So if we have 1 liter of solution, we can find a certain number of moles of sodium chloride. If we have a certain number of moles of sodium chloride, we can find how much solution I have if I have it at a certain molarity. So let's look at this over here. So basically preparing a solution of a specified concentration. So if we wanted to prepare a 1 molar sodium chloride solution, this is what we would do. Okay. First, we weigh out 1 mole of sodium chloride. Well, we can know that we have 1 mole of sodium chloride using our molar mass of sodium chloride. So our molar mass is 58.44 grams. So what we do is we weigh out 58.44 grams of sodium chloride into our volumetric flask. That's what this is. After we weigh out 1 mole, or 58.44 grams of sodium chloride, again, that is the molar mass. We add water until the solid is dissolved, and then we add additional water until the 1 liter mark is reached. So this is a 1 liter volumetric flask, so that means I add water until we reach 1 liter. So I have 1 liter of water mixed with 58.44 grams of sodium chloride, and so this is how we can make a 1 molar sodium chloride solution. And that's what that means. I have 1 mole of sodium chloride dissolved in 1 liter of water. Now, this is what happens with the solute and the solvent. We're going to look at this in a second, but basically what happens is the solute expands, the solvent expands, and the solute and the solvent mix together to get in between each other. So that's what happens when it actually dissolves. Because molarity relates the moles of solute to the liters of solution, it can be used to convert between the amount of reactants and or products in a chemical reaction. The general conceptual plan for these kinds of calculations begins with the volume of a reactant or product. So here we have the molarity of a solution. I'm going to try this, but I'm doing this on my computer, not my iPad, so we'll see how this goes. It says, what is the molarity of a solution containing 25.5 grams of potassium bromide dissolved in enough water to make 1.75 liters of solution? So remember what molarity is. So molarity is moles of solute over liters of solution. Okay, so now we have grams of potassium bromide, that's our solute, but we don't have moles, so we have to convert grams to moles, and we use molar mass. So we have 25.5 grams of potassium bromide, and again, I'm doing this on my computer, so bear with me here. Potassium bromide. Okay. Now, we're going to divide by the molar mass of potassium bromide to find the number of moles. So that's going to be 119.002 grams per mole. And this will give us the number of moles of potassium bromide I have, because I need to use the number of moles of potassium bromide to find the molarity. So 25.5 divided by 119.002, and that's going to give us 0.214 moles of potassium bromide. Okay, so we have 0.214 moles of potassium bromide. So we do 0.214 moles divided by, now we have a we want to make 1.75 liters of solution. So 1.75 liters of solution. Okay, so we divide that by 1.75, and so our molarity is going to be 0.122 molar, which is going to be that M, potassium bromide solution. And so I'm going to put potassium bromide, and then I'm going to put aqueous, AQ. Oops, that should be an A. Erase that. So that should be AQ. That's a parentheses. AQ. Okay. So that is a 0.122 molar potassium bromide solution. Okay. Now, often solutions are stored as concentrated stock solutions. So in my closet right now, I have a 15 molar nitric acid solution, which we don't want to use 15 molar in the lab, because 15 molar is incredibly damaging. It will slough off your skin. But that's a stock solution. So what I can do is I can actually dilute that 15 molar to, say, maybe a 3 molar solution with water that we can actually use in the lab. So to make solutions of lower concentrations from these stock solutions, more solvent is added. So what I do is I take that 15 molar nitric acid solution, and I would dissolve enough water in it to make it a 3 molar solution. So the amount of solute doesn't change, just the volume of the solution. So the moles of solute in one solution equals the moles of solute in solution 2, but the volumes are going to be much different. So the concentrations and volumes of the stock solutions and new solutions are inversely proportional. So basically, this is the formula I would use to find how much solute I would need to add to get my molarity. So say I had, like I said, I had a 15 molar solution, and say I wanted a 3 molar solution, and I wanted 500 milliliters of 3 molar, okay? Or we'll say 0.5 liters, so 0.5 liters, okay? So say I needed 0.5 liters of a 3 molar solution, but I have a 15 molar stock solution. I need to find how much of that stock solution that I need to measure out to get me half a liter of 3 molar. And so what I do is I just divide both sides by 15 molar to get that V1. And what this V1 will tell me is the volume of my stock solution that I need to add. So 3 times 0.5 divided by 15, that gives me 0.1. So that means I need 100 or 0.1 liters or 100 milliliters. So I would have 100 milliliters of my stock solution, and I would add 400 milliliters. I would add 400 milliliters of water. Okay. So I have 100 milliliters of my 15 molar stock solution, right? 15 molar stock solution. Add 400 milliliters of water, and that gives me 500 milliliters of 3 molar solution. Okay, I hope that makes sense. I'll probably add a link to a video that kind of goes more into this, just because I can't really write on my computer. So let's talk about types of solutions. So solutions in water is dissolving medium. Solutions in which the water is the dissolving medium is called aqueous solutions. Any substance whose aqueous solution contains ions is an electrolyte. Any substance that forms a solution containing no ions is a non-electrolyte. So the key word to that is electro. Think of electricity. Ions, or electricity requires ions, or the flow of electrons, for it to happen. So if my solution contains ions, it's an electrolyte. If it does not contain ions, it's a non-electrolyte. Electrolytes that are present in solution entirely as ions are strong electrolytes. This means that they have completely dissolved in the solution. Whereas those that are present partly as ions and partly as molecules are weak electrolytes. So it does not completely dissolve in the solution. Electrolytes are substances that would generate electricity in solution. This is explained by the presence of ions in the solution. Now, strong electrolytes, so that electrolytes that completely dissolve, include soluble salts, strong acids, and strong bases. These completely dissociate in the solution of water to dissolve. Dissociate in a solution of water. To dissociate is to split up into its cations and anions. An example of a strong electrolyte would be hydrochloric acid or hydrogen chloride. And when it's dissolved, the hydrogen ions are split apart from the chlorine ions, and that creates hydrochloric acid. Now, weak electrolytes include weak acids and weak bases. These partly dissociate, meaning they partially dissolve in a solution of water. So only some molecules will split up into their ions, which explains why they are present in both ions and molecules. Non-electrolytes are molecular compounds in which do not conduct electricity. An example would be sugar. So here's an electrolyte solution. This is a salt. You have positive and negative ions. Here is a non-electrolyte solution. You have sugar. Now, sugar still dissolves, but what happens is the water overcomes those intermolecular forces, not the ionic bonds. Now, this would be an example of a weak electrolyte. So we have magnesium ions, potassium ions, iodide ions floating around, and we have magnesium phosphate that is not dissolved. So we have some magnesium dissolved, but some not dissolved, and therefore it's a weak electrolyte. Now, when discussing solutions, colligative properties are properties that depend upon the concentration of solution, concentration of solute, molecules, or ions, but not upon the identity of the solute. For example, a solution of 6 molar sodium chloride would act like differently than simply pure water. So basically what happens is these colligative properties are properties that are associated with a concentration of a solute. And so when you have salt, that means that salt water, so a solution of sodium chloride dissolved in water, is going to act differently than actual water. And there are 3 different ways it acts differently. When I dissolve salt in water, it lowers the vapor pressure, it raises the boiling point, and it lowers the freezing point. So let's look at vapor pressure lowering. So when a solute is dissolved in a solvent, you decrease the tendency for water molecules to evaporate in the gas phase. This means that there will be less gas above the surface of the liquid, leading to a lower vapor pressure. There's a formula for finding the exact new vapor pressure. It's called Raoult's law. So basically what happens is when I dissolve salt in water, water is not going to evaporate as quickly. So what happens is it lowers that vapor pressure and makes the water not evaporate as quickly. The intermolecular forces, think of what's happening inside that water. So before we dissolved salt in water, water had hydrogen bonding, right? But when we dissolved salt in that water, it had that ion dipole bonding. So the ion dipole intermolecular force is going to be stronger than the hydrogen bonding that was just in pure water. Therefore, the vapor pressure is going to be lower. Not as many is going to evaporate out. So this is Raoult's law. I do not think you're going to have anything that makes you calculate Raoult's law, but again, it's good to know just in case. So the pressure of the solution, or the vapor pressure, equals the X of the solvent, which is the mole fraction of the solvent, times the vapor pressure of the pure solvent, so times the vapor pressure of the water. So what it is the moles of solvent divided by moles of solvent plus moles of solute. That's how we find the mole fraction. Now, another way that solutions change these colligative properties is they elevate the boiling point. So when you dissolve salt in water, it will elevate the boiling point of water. So applying a non-volatile solution decreases the solution's vapor pressure by Raoult's law. Then the temperature must be increased to return the vapor pressure to a pure solvent value. This means as you add more and more solute, the temperature at which the solution boils increases. A good example of this is when you make pasta. Chefs around the world always recommend that you salt your water before you add pasta. And while this is, of course, adding flavor, it also raises the boiling point of your water, making your pasta cook quicker. So what happens is it makes your water, you have to wait longer for your water to boil. But what happens is that water is boiling at a higher temperature, and so your actual pasta will cook quicker. This same principle is seen in chemistry with solutions. There's another formula to calculate the exact elevation. So it's delta TB equals Km, where delta TB is the change in the boiling point. K is a specific constant. I think it's the boiling point elevation constant. And M is the molality of the solute. So not molarity, but molality. Concentrations can actually be measured differently. And we'll talk more about this later, but molality is a measure of concentration, that is moles of solute over kilograms of solvent. Now, the last thing that happens is it lowers the freezing point. So when you add salt to water, it lowers the freezing point of water. The same applies for freezing points of solutions. As boiling point elevates, freezing point depresses or lowers. This means that, for example, a solvent may have a freezing point of 0 degrees Celsius without any solute. And then once you dissolve some solute, the freezing point will lower to negative 1.5 degrees Celsius. So an example of this is adding salt to roads. So when roads freeze over, what happens is they'll come around and they'll add salt to that ice. And it melts the ice because that solution of salt and water is lowering that freezing point. And so it melts the ice on the road to make it water again, to make it that solution. So the formula for freezing point depression is very similar to boiling point. So again, it's the freezing point is the change in the freezing point. So this is not the actual temperature. This is just how much it changed. equals negative K, again, where it's that specific constant, and M is the molality. Now, there are many different methods in which we can separate a mixture. Some of these you have done, some of these you've probably heard of, some of them you haven't. So, first one is evaporation. So, evaporation is a process by which a solvent is boiled and thus evaporated in order to separate a solute. For example, if you boil salt water long enough, you will be left with a small amount of salt in your pot. So, again, you've probably done... you know what evaporation is. If you leave a pot of salt water on the stove for long enough, eventually all of the water is going to evaporate out and salt's going to be left over. There's filtration. So filtration is also a simple one to understand. When filtering a mixture, one runs the mixture through a porous barrier. With this barrier, the liquid passes through, but the solid remains in the filter. So we have done this. The first lab we did with the hardness of water, we did a filtration lab. The next is chromatography. You may or may not have done chromatography, but it actually has to do with differences in intermolecular forces. And we will do a chromatography lab later on. Chromatography is a process used to separate solutions of multiple liquids by using an absorbent solid like paper and an appropriate liquid. Typically a non-polar solvent, so usually it's not water, it's usually something like ethanol. But a solvent like water is also possible. Paper chromatography has the solvent traveling up the paper, essentially dragging each part of the solution away from itself via differences in intermolecular forces. So basically what happens is these chemicals, as the solvent goes up the paper, so they put the paper in the solvent, and as the solvent goes up the paper, chemicals are separated because they travel at different speeds because of intermolecular forces. So the solvent usually, or the color or the solute that's usually lower is not as attracted to the solvent as something that's a little bit higher. So remember, like dissolves like. So if this is a non-polar solvent, then what's on top can be assumed to be non-polar because they attract each other, whereas down here it'd probably be a polar solvent. Now the last one is called distillation. And again, you may or may not have heard of distillation, but like chromatography, it is used to separate solutions of liquids. With distillation, the fact that different liquids have different boiling points is taken advantage of. Through distillation, a solution is carefully heated such that only one liquid boils out and then recondenses into another beaker. So basically, one of the boiling points in this solution has one of these parts of the solution has a lower boiling point than the other. Ethanol has a lower boiling point than water. So it's heated to 74.4 degrees Celsius, so that's lower than water. So the water is not boiling out, but the ethanol is. The first liquid to boil is the one with the weakest intermolecular forces, again, because if it has a lower boiling point, a weaker intermolecular force, and it increases as the boiling point increases. This traditional form of distillation is called fractional distillation. Distillation can also be used to recollect the liquid in evaporation separation. This is called simple distillation. And so if it is evaporation, that just means that it's not heated. It's just going to eventually evaporate out into the ethanol. And so this is when we're actually heating it to its boiling point. This is evaporation. Eventually the ethanol is going to evaporate out. So what happens when a solute dissolves? So let's actually talk about solubility. So solubility is basically the ability for something to dissolve. And so there are attractive forces between the solute particles holding them together, and then there are also attractive forces between the solvent particles. When we mix the solute with the solvent, there are attractive forces between the solute particles and the solvent molecules. So basically what happens is there are attractions between the solute and solvent. There are attractions between the solute and solute, and there are attractions between the solvent and solvent. But when we dissolve the solute in the solvent, there are attractions between the solute and the solvent. If the attraction between the solute and the solvent is strong enough, the solute will dissolve. So if the attraction, say, between the salt and the water is strong enough, the salt will dissolve in water. So when sodium chloride is put into water, the attraction of the sodium and the chloride ions to water molecules competes with the attraction among the oppositely charged ions themselves. So Each ion is attracted to the surrounding water molecules and is pulled off away from the crystal. When it enters the solution, the ions are surrounded by water molecules, insulating it from other ions. So that's what's happening here is the water molecules are coming in, they're pulling those ions apart and dissolving those ions. The result is a solution with a free-moving, charged particles able to conduct electricity. A solution of salt, an electrolyte, conducts electrical current. A solution of sugar, a non-electrolyte, does not. Ionic substances such as sodium chloride that completely dissociate are strong electrolytes. So we've talked about this. They completely dissolved. Except for acids, most molecular compounds are non-electrolytes. That means that they do not create ions. Acids ionize in varying degrees in water. Those that don't completely ionize are called strong acids, or those that do completely ionize are called strong acids. Those that don't or don't completely dissolve are called weak acids. Now, acids are molecular compounds that ionize when they dissolve in water. The molecules are pulled apart by their attraction for water. So when these acids ionize, they form hydrogen ions, hydrogen cations, and also anions. So that's the biggest thing is when acids dissolve in water, they form those ions. The percentage of molecules that ionizes varies from one acid to another. So acids that ionize virtually 100% are called strong acids. Now, acids that only ionize a small percentage are called weak acids. So basically what happens is strong acids completely dissolve, whereas weak acids only partially dissolve. So here is acid strength. So acid strength basically has to do with how much is actually ionized. We'll look in that later on. But basically weak acids obviously don't completely ionize, so they would have a lower acid strength, whereas strong acids completely ionize, so they have a higher one. Now, let's talk about solubility rules. Okay, these solubility rules are very important, very, very important. You have to memorize them, period. When an ionic compound dissolves in water, the resulting solution contains the intact ionic compound itself, but its component ions dissolved in water. However, not all ionic compounds dissolve in water. For example, silver chloride remains a solid and appears as a white powder at the bottom of the water. In general, a compound is determined soluble if it dissolves in water and insoluble if it does not. Precipitation reactions are reactions in which a solid forms when we mix two solutions. So we're going to talk about this next unit in chemical reactions, but basically when two aqueous solutions of ionic compounds come together and they produce this compound that is insoluble in water, that compound is called a precipitate. Okay, and we can predict if it's going to form a precipitate or not by these solubility rules. Precipitation reactions do not always occur when two aqueous solutions are mixed. Nothing happens when we combine solutions of potassium iodide and sodium chloride because of these rules. So let's look at these rules. So the top part, it says compounds containing the following ions are generally soluble. So meaning compounds containing these ions are usually soluble unless it has exceptions. So compounds that contain lithium ions, sodium ions, potassium ions, ammonium ions are always soluble because there are no exceptions. So those are always soluble. Nitrate ions and acetate ions, again, are always soluble. There are no exceptions. So if you have a nitrate or an acetate, soluble. Chlorides, bromides, and iodides are always soluble, period, unless they are paired with silver, magnesium, or lead, then they are insoluble. So if you have silver chloride, magnesium chloride, lead chloride, they're going to be insoluble. Otherwise, they're going to be soluble. And then sulfates are always soluble unless it's paired with strontium, barium, lead, silver, or calcium, then it's going to be insoluble. But say it's paired with sodium sulfate soluble. Now, everything under here is going to be generally insoluble. So this is the opposite. Hydroxides and sulfides are generally insoluble. They do not dissolve in water unless they're paired with lithium, sodium, potassium, or ammonium. Because remember, any of these, there are no exceptions, meaning that they're always going to be soluble. When a sulfide is pairs with calcium, strontium, or barium, it's always soluble. And when hydroxides pairs with calcium, strontium, or barium, it's always slightly soluble, meaning it's a weak electrolyte. Carbonates and phosphates are always insoluble, again, unless paired with that lithium, sodium, potassium, or ammonium. So you need to memorize this table. It is incredibly important you memorize these solubility rules.